All right, good morning. So, although almost nobody's here yet, let us start. And so I'll start just recapitulating what we have done last time. So the first lecture we discussed thermodynamics of asymptotically flat black holes. Okay, and the key thing to take out from there was that you can associate the temperature of the black hole with the surface gravity and the entropy of the black hole with the area. But then I told you that maybe asymptotically flat black holes are, well, they are more realistic, but the thermodynamics is not that interesting. And for that reason, we started discussing these black holes in anti-de Sitter space. And the anti-de Sitter space is very, very weird because it acts like a confining box. It looks like a cylinder. It has a nice time-like boundary. And then, typically nothing that is inside the ADS space can escape. Right? So for time-like particles, this is guaranteed by this gravitational pull towards the center. For null particles, you guarantee that by imposing reflective boundary conditions and so on. And as a result, your ADS space will actually be unstable. Nevertheless, if you put a black hole inside the ADS space, and this is an example, then everything is nice and stable and so on. Okay, so Schwarzschild ADS black hole will be stable. If you slightly perturb it, you just settle down to a similar configuration with just slightly modified mass and so on. So what is the new feature here for black holes in ADS is that they can feature different topologies of the horizon. So whereas in asymptotically flat case, you only have spherical horizon topologies, it looks like a sphere. Even Kerr, who's slightly deformed, it looks like topologically like a sphere. But here you can have planar horizon, you can have more complicated horizons as well. So that's what that K stands for. You also have different asymptotics. Of course, if I go with R to infinity, to the spatial infinity, I am recovering that my metric function f doesn't approach 1, as I'm used to in asymptotically flat case, but it approaches R squared over L squared. So that precisely corresponds to this ADS asymptotic. So it blows up. So now you can start adding charges and rotations, as we will do in a minute. Of course, this is the theme of the course, but one thing which was very interesting for us, I think, is that if you consider the gravitational action in ADS, then you have now a very nice covariant prescription for how to calculate it. And so instead of this vague background subtraction, you have now these beautiful ADS counterterms, which is the second line over there. And so everything is expressed in terms of the invariance on the boundary. Okay, so I have something like a cosmological constant on the boundary. I have the Ricci scalar on the boundary, and so on and so on. And so including these terms guarantees that your action will be nice and finite and well-defined in the sense that it yields a well-posed variational principle with Dirichlet boundary conditions. So it's enough to impose delta HAB on the boundary is equal to 0 and satisfy the Einstein ADS equations in the bulk, and it gives you that the variation of the action is equal to 0, right? But also it gives you this beautiful quantity. It's like, by definition, you've seen this definition of the energy momentum tensor, right? Right. So this is basically a definition of the energy momentum tensor. I vary the action with respect to the metric. Whatever stands here is the energy momentum tensor, right? And this will be automatically symmetric because this guy is. So it's a symmetric tensor, but also it will be covariantly conserved because if you start with an action which is diffeomorphism invariant. If you have diffeomorphism invariant action, then this tau AB will automatically satisfy nabla A tau AB equals to 0. So it's really a nice energy momentum tensor. And then, this is like a boundary energy momentum tensor. This is the explicit prescription for the tensor. But we can start calculating the associated conserved quantities with this tensor, in particular the energy. And if you calculate this boundary energy, it will give you the total energy, total mass of the spacetime. So this gives you an alternative way as to how you can calculate the mass of the black hole, for example. It's a holographic mass, holographic construction. So now there was a question last time whether this is... So in principle, you can consider various conformal frames for your boundary metric. We will talk about it in 2 lectures or whatever. And whether this prescription for the energy is independent of which frame you choose, and the answer is, of course it is. So no matter which omega conformal scaling of the boundary metric you choose, your energy will be independent of that, and then it'll give you the energy of the space-time. Okay, if you don't know what I'm talking about, that's fine. You will see it in a couple of lectures. Okay, so that's that. So now what is beautiful, perhaps the most beautiful about the ADS black holes is that they feature really interesting thermodynamics. Okay, and so let me just discuss that for the simplest black hole, which is this Schwarzschild ADS black hole with spherical horizon topology. So I'm choosing k equal to +1, right? And this is my metric. So now what you can do is that you can calculate its thermodynamic quantities as we discussed. So for example, the temperature is just F prime evaluated at R plus divided by 4 pi. You can put an absolute value, it doesn't matter. Here it will be positive. Okay, and that gives you the temperature over there. You would obtain it by this Euclidean trick by requiring regularity of the Euclidean action. You can calculate the free energy, okay, either from the gravitational action, right? So that's what we discussed before. Or you can simply say, well, the free energy, well, it's an internal energy, in our case mass, minus Ts. Okay, that's a shortcut for that, right? This is just a Legendre transformation of the internal energy. Internal energy of the space-time is the mass, minus Ts must be that. So you can check that this is true. So you have that. So now you see, this is an explicit expression for these quantities in terms of the ADS radius L and the horizon radius R plus, and that's like that. What you typically do is that you fix cosmological constant. So you fix L, and then this is a function of R plus, and this is a function of R plus. Okay. So now what you can do is that you can parametrically plot, as you change R plus, how G depends on the temperature, right? So I just choose R plus equal to 1, and I get G equals to something and T equal to something, and I get a point. So I can plot G and T diagram. So you are plotting the free energy as a function of temperature, of its thermodynamic variable. And you will do it in your homework. Did you get the homework already? Not yet? Yes, you did. Okay, perfect. So then you already know what I'm talking about. And this is what you get. You get something which is a little bit more interesting than what happens for Schwarzschild without ADS. You get a curve like this. Okay, so now I told you we are plotting this parametrically. So this is how the R plus is increasing. Okay, so you have teeny tiny, so you have small black holes here. Small black holes here, R plus is very, very small. And then you keep going, and then something strange happens here. There's like a cusp in the free energy, and then you keep going down, and so you have large black holes here. Large black hole here, right? So basically, this point here sort of distinguishes, like, am I talking about a small black hole in this branch, or am I talking about a big black hole in that branch? What does that mean? How can I talk about small black hole or large black hole? It's because you have another scale in the problem. That's the ADS radius. Okay, we have this L here, which we fixed. So typically what you could say is that small black hole is something like R plus smaller than L, and large black hole will be something like, so this will be large, that the radius of the black hole is bigger than L, roughly speaking. Okay? So you have another scale, and then you can compare with respect to this scale, and either I am small or I'm big, and depending on which one, the behavior is very, very different. Okay? So now apparently, if you have teeny tiny black hole, right, the R plus is really, very small, much, much smaller than L, well, the teeny tiny black hole really doesn't know about that it is contained in ADS. Like the ADS scale is much, much larger, so the small black hole will behave like Schwarzschild. Okay? So this is precisely this branch. So if you had Schwarzschild, this thing here would just continue like that. That would be the free energy of Schwarzschild. Okay, so for small black holes, they don't know that they are in ADS and they behave Schwarzschild-like. In particular, their specific heat will be negative. Okay, that's what I told you the first lecture. However, if you have large black holes, well, if the radius is bigger than L, well, certainly the black hole knows about ADS, right? right? It has to deal with the ADS. And that's why the behavior is very, very different. It's this branch of large black holes, and it's very, very different. The specific heat actually is positive for this branch of the black holes here. Okay, very, very different behavior. So what you can say is that these large black holes are at least locally thermodynamically stable. They have positive specific heat. These ones, they are Schwarzschild-like, they have negative specific heat. They cannot be in thermal equilibrium, but these ones can be. Moreover, the large black holes, if I fix the temperature, you always want to minimize the free energy, globally minimize the free energy, and that's your preferred thermodynamic state. So of course, this one is smaller than that one, right? So actually, it should be the large black hole which is thermodynamically preferred to the small one, and it's the stable one. Okay, so really, the large black holes are thermodynamically preferred to the small ones, which are moreover unstable. Okay, so this is what it is, and it's quite interesting. But this is not the whole story. The whole story is that you should be also thinking about that your system, thermodynamic system, is not only a black hole, right? You should be thinking that this black hole radiates away a Hawking radiation at that given temperature. And so then you might be thinking, well, what if I have a system which also includes this radiation? Okay, so I have my thermodynamic system is radiation plus black hole. So now you see that for temperatures smaller than this thing here, so I have this cusp here. So if I'm for smaller temperatures than here, you cannot have a black hole, right? I don't have a curve there for a black hole. So black holes do not exist in ADS for very, very small temperatures like this, below that. What can exist there, however, is the radiation, right? So what you can do is that you can fill your ADS space with radiation. Now, Hawking and Page calculated how much radiation you can put in the ADS space so that it's in equilibrium. It's like a black body radiation or whatever. It's not much, but certainly, the radiation is not much. The mass of the radiation is small, and the entropy is small of this radiation. Okay, so it's sort of like if you calculate it, it sort of goes like a little bit like that. But when compared to the black hole, free energy or entropy or whatever, it's really teeny tiny. Okay, so that's why people say, well, you can say that the free energy of that radiation is basically zero. So this is your radiation free energy. Okay, and then you immediately see that if you combine the system black hole plus radiation, then if you want to globally minimize the free energy, that all the way up to here, the free energy of the radiation is smaller than that of black hole plus radiation, which is zero. Okay, but here, the large black hole has smaller free energy than radiation. Radiation keeps going like this at zero, sort of, and here the black hole goes like really, really negative and crazy. So this is a thermodynamically preferred branch. Wow, that's amazing, right? So what it means is that if I start with a small temperature and I have ADS filled with radiation, and I keep rising the temperature of the system, well, I'm happy as radiation to some point. But here, when I reach this special temperature, Hawking-Page temperature, then I want to jump and become a black hole. So the radiation sort of collapses and forms a black hole. Okay. So now, how does that happen? Is that you have the free energy, which is continuous. Here, the minimum is continuous, but the derivative is not. You have derivative like that, and you have derivative like that. That's a characteristic of a first-order phase transition. Okay. So at T Hawking-Page, there will be a first-order phase transition from radiation to large black hole. Okay, so most famous black hole thermodynamic phase transition there is, and it's a phase transition between radiation phase and large black hole phase. Yes?
Is there some sense in which this temperature is related to like the density of the photons becoming critical in some sense, like?
Density of the photons becoming. So this is not like you shouldn't be thinking about this collapse of radiation to black hole as a classical collapse due to gravity. You should be thinking about like a thermodynamic phase transition, more like a tunneling process or something like that. So it's like semi-classical process of. This is thermodynamics. It's not classical. Okay, so it's semi-classical. So yeah. But you can show that for a given temperature, like to keep the radiation in thermal equilibrium in ADS, like Hawking and Page, they have precise estimates how much radiation you have to put there, and it's not much. So like the density is not very high. Yeah. So anyway, so there's this first order phase transition from radiation to large black hole. It happens when the free energy of the black hole becomes 0. Okay, if you look at the free energy of the black hole, which was the previous formula here, this thing here must become 0. Well, the only possibility is that R plus equals to L. Okay, so it happens when R plus exactly equals to L, in which case the temperature, if I plug R plus to L, is 1 plus 3 is 4 divided by 4, so it's 1 over L, pi L, and that's the Hawking-Page temperature. Okay, so this is when it happens. But now I told you that there's this beautiful duality between what happens in the bulk space-time with what happens with your boundary quantum field theory. And so this, first-order phase transition should correspond to some first-order phase transition in your dual quantum field theory. And that was discussed by Witten and whatever, that maybe, this could be a prototype of a phase transition which happens for quark-gluon plasma if you have from confinement to the confinement phase of this quark-gluon plasma. Okay? So this is due to Witten and other people. Right? So I think I fulfilled my goal. We can stop the course here. So now if you go to a string theory conference or ADS CFT conference, people will talk a lot about Hawking-Page phase transition. So now you know what's going on, okay? And so that was my goal, so we can stop the course here. Just to impress you, if you add charge to that, okay, so now I don't consider Schwarzschild ADS, but I consider Schwarzschild ADS plus charge, in which case metric function is 1 minus 2m over r plus r square over L square plus q square over r square. That is my metric function. Like it will be Reisner-Nordström plus ADS. Right? So if I just add charge, something even more interesting happens. In fact, what you get is a free energy. So it was first discussed by these people here, Rob Myers in particular. But if you plot the free energy, here, then it looks even more interesting. It develops this piece. So the radius from the black hole increases like that, like that, like that. Okay, so you get something which is called swallowtail behavior, right? So again, so I'm increasing like this. This is the free energy. That's the temperature. Again, the cosmological constant is fixed, and also the charge is fixed. And so you go like this, you go like that, and you go like that. Okay, so that's your behavior as the radius increases. And now again, you want to globally minimize your free energy. So you want to be here. It's a small black hole. But instead of going like this, like that, you immediately go down. And that will be a large black hole. Large. And there's a small one. Okay, so there will be a phase transition from small black hole to large black hole. In this case, if you have charged black hole. That was for one particular value of lambda. But now, if you start changing lambda, what happens is that this swallowtail is diminishing. And for some particular lambda, it will just be like a 1 point. And then above that thing, there will be just smooth, nice free energy. Now, what this point corresponds to is precisely when your first order phase transition degenerates to a second order one. In this case, the free energy is continuous, but also the first derivative is continuous, right? So this will be like a second order phase transition. And it's like a critical point, okay? And the same thing exactly happens when you discuss van der Waals gas and stuff like that. So this is what happens for black holes. You have small black holes and large black holes. this is what happens for liquid-gas phase transition. And similar, so then you can plot the corresponding phase diagram, right? How do I do that? So I fix lambda to plot this, and then for that given lambda, I have this temperature here where the first order phase transition happens. And then for different lambda, I have this temperature here for which the first order phase transition happens. And then finally, I have the temperature for the critical point. Okay, so you can plot a lambda T diagram, right? And it will give me like these points, and there will be finally a critical point where it terminates. This is what you get. Okay, for black hole case, you get a phase transition small black hole to large black hole. This is exactly the line, coexistence line between the two phases. And it terminates at a critical point where it's the second order phase transition. And above that, the free energy is smooth and you cannot distinguish the two phases. And this is what would happen if you compare it to Van der Waals analogy, Van der Waals gas, and it looks exactly the same. So people actually like to talk about that there's like this Van der Waals analogy, or Van der Waals behavior of charged ADS black holes. Interestingly, if you've taken some statistical physics course, you know there's something which is very important and people concerned about it is critical exponents for second order phase transitions, right? So basically like how physical quantities behave if you are close to this critical point, right? How the specific heat behaves, how it diverges or whatever, right? How physical quantities behave in the vicinity of the critical point. You can show that both black holes and Van der Waals gas have the same critical exponents, which are the mean field theory critical exponents for the Ising class and stuff like that. They are given over here. So really, it seems like the black holes belong to the same universality class as Van der Waals.
This is only in 4 dimensions, or?
This will be true. It's a very good question, because what you are probably hinting on is that mean field theory is exact if you go above 4 dimensions or whatever, but 4 spatial dimensions. So this will be true for black holes in any dimension. So somehow the mean field theory prescription works for black holes. Like Roberto Emparan will tell you, well, because you are using geometric description of gravity or whatever, you cannot go beyond mean field theory and stuff like that. So I don't know. All right. So more interestingly, if you go to even more interesting black holes, so all we just did so far, we added charge, but you can add rotation, you can consider more complicated black holes, you can get more interesting phase diagrams.
So in the ordinary phase diagrams, there is a coexistence region, right?
Stupid. Okay, say it again.
That in the ordinary phase diagrams of like liquid, gas, and so on, there is a coexistence region. And what does this mean for the black hole?
Oh, it's a very good question, right? I don't know. So certainly for liquid and gas, what it means is that I have evaporated a little bit of my liquid, right? And then I still have something left to evaporate. So I'm coexisting. So what it corresponds to is precisely these oscillations in the PV diagram, right? So you have like P and then V diagram, and then this is the behavior of your isotherms, which you know, and you know that the phase transition happens like you have to do like a shortcut here, where this area is equal to that area and stuff like that, right? This Maxwell's equilateral, right? So what was happening here is that I am sort of like gradually evaporating the liquid and stuff like that. So here you have some weird superposition of small black hole and large black hole. I don't know. It's a very good question.
And also, so I think that there is some sort of domain wall, and when I go from small to large black hole, is like some bubble nucleation or something.
You could think.
The analog in the...
You could think about it like that. Yeah, you could think about it in the Euclidean setting, like a tunneling of one thing to another. Yes. All right. So just to tell you, there are many other phase transitions which you can see for more complicated black holes. You can see a triple point, something like solid liquid gas phase transition, if you have rotating black holes and so on. If you're interested, you can look at my paper. Okay. Here we go. Summary. So ADS black holes, very interesting. Okay. From thermodynamic perspective, very interesting. From classical perspective, also interesting. You have various topologies, horizons. You have more possibilities, right, and so on. ADS action, beautiful. right? Asymptotic deferred reduction, we can do it, but it's painful, and there's this background subtraction and so on. ADS action, so beautiful. Okay, you have covariant prescription. It gives you a way to define this holographic stress tensor, and that holographic stress tensor gives you a way how to calculate quantities associated with your spacetime, in particular the mass. ADS black holes feature very interesting phase transitions. You have this Hawking-Page phase transition, you have this van der Waals-like phase transition, and so on. All these phase transitions will somehow, through this duality, ADS-CFT duality, give you some kind of phase transition on your QFT side, right? So you can sort of predict these things for QFTs. And that's basically it. So, questions? That's thermodynamics of black holes in ADS. Questions? No questions. All right. So now, very good. So let me now go to chapter 2. This was like a motivation from the black hole thermodynamics. Now let me do a motivation from string theory on the ADS-CFT. And there will be just, as I said, as I advertised, there will be like 6 cartoons about string theory with a little bit of comments. So chapter number 2, if you want, motivating ADS-CFT from string theory. Or if you want string theory in 6 cartoons. So what is string theory? String theory is a quantum theory of interacting relativistic strings. It's a quantum theory of interacting relativistic strings. But then it was discovered later that actually it's not only the strings which are there, but also higher dimensional objects like branes and stuff like that. So it's not only relativistic strings. String is one-dimensional object, but you can have more higher dimensional objects. And higher dimensional objects. Okay? And that's what it is. So now let me start discussing. You've probably seen this in many courses, but let me just review that. Let's just talk about, well, you have quantum theory of relativistic strings. So let me start with what a relativistic string is. Okay, so let me do a classical thing. So let's call this like classical strings. And let me do an analogy. So we know what a particle is, relativistic particle. So if you have relativistic particle, there's something like time here, and you have the space here. So time and space. And then you know that if you have relativistic particle, it's something like a point-like object, which sweeps out something, a trajectory x mu of tau. Okay, so we have a particle like that. That particle moves in our space-time, and there will be the corresponding word line of the particle. Line of the particle. And what we also know is that this word line of the particle, if you have like a free particle, it follows the geodesic in a given space-time. And geodesic is defined such that if you calculate the length of this word line between like 2 points, then geodesic is such that it's an extremum of this length. It not necessarily be a minimum, but it's an extremum. So you extremize the length. Okay, so for point particle, so S of point particle depends on the trajectory. If you have free particle, it's just an extremum of the length, you can say of the proper length or proper time, right? So it's an extremum of the proper time if we have time like motion of the particle, right? And you can write it in terms of some parameter. Maybe, you know, I can write x mu of tau, but also I can write tau as a function of lambda, which will be some other parameter. So proper time as a function of lambda. So then it's an integral of minus m0 and then minus eta mu nu dx mu d lambda dx nu d lambda square root of that d lambda. Right? You have seen this. And so we are just extremizing, you know, this proper time here, proper length of that thing, and it's written like that. So now look at something which you have eta mu nu, and then this thing here. It's a scalar quantity. Okay, that's easy peasy. It's a scalar quantity here. Let's denote this scalar quantity as gamma lambda lambda. Why not? Right? It's something which, well, it depends on lambda. There's only one component, gamma lambda lambda. Oh, why not? So let's call this gamma lambda lambda. It's a scalar quantity. It's a number. Well, it's a function. Right? So now what is true is that if you take determinant of the function, you get the same function. Okay, very good. So what you can also write this as this is equal to minus m0 integral square root of minus determinant of gamma lambda lambda d lambda. So I made it more complicated, but makes sense, right? So I just made a definition of this gamma lambda lambda, and I'm saying, well, determinant of gamma lambda lambda is gamma lambda lambda, so I can write it this way. So now what is this gamma lambda lambda? Well, what is it I'm doing? I am taking my Minkowski metric in my, let's say, I have the overall Minkowski space here. Eta mu nu, right? So what I'm doing here is that I am taking this Minkowski metric, and each index mu and nu is projected down by this beast over here, dx mu over d lambda. What is dx mu over d lambda? It's a projector onto my word line trajectory. So dx mu over d lambda, dx mu over d lambda, d lambda is like a projector. So what does that mean? It means that I am projecting my Minkowski metric into the metric on my word line. And I'm projecting this index, and I'm projecting that index. That's what. So what this gamma lambda lambda is like an induced metric on my word line trajectory. Okay, so gamma lambda lambda is an induced metric. This is getting too small, I'm sorry for that. But gamma lambda lambda is an induced metric. And then, you know, what this is telling you is that I'm just taking the induced metric on my word line trajectory, I calculate this determinant, well, and take a square root, and that gives me the proper length of that word line trajectory. And this is what the point particle action is. Everybody happy? You've seen this many times, right? So very good. So now if I want, instead of a particle, I want a string. So this would be a particle. If I want a string, it will be a time and there will be space. So now at a given time, my string is an extended object. It's like, it goes from here to there. It has some weird shape, but that's what it is, right? So at a given time, the string will look like this, right? And then, as the time evolves, the string, as it moves in time, it sweeps out a worldsheet in the space-time. Okay, so this will be like a worldsheet in the space-time. How do I parameterize, what's happening on that worldsheet? So first of all, worldsheet, how many dimensions it has? So here, my world line was one-dimensional, right? It was just point sweeping out a trajectory. Here, I have a line of points sweeping a trajectory, so it will be two-dimensional, right? So worldsheet will be, in our case, will be two-dimensional. So I should be able to introduce some coordinates on this worldsheet, two coordinates which parameterize where I'm there, right? So let's consider these psi a coordinates. Let's call them, I don't know, tau and sigma, or lambda and sigma, whatever. So these will be my coordinates, tau and sigma, which tells me where I am on that worldsheet in this two-dimensional sheet, right? And if I want to describe how this sheet looks like in my Minkowski space, what I need to provide is, like, I want to describe this point. That point has, some coordinates in my Minkowski space, x mu, and how they behave as a function of this psi a, right? I have this description here. Okay, so that's what my description of a one-dimensional object will be. So now, if you want to describe a motion of a free string, you may think, well, here, if I have free particle, I want to extremize the length of the world line. Here, you may want to extremize the area of the world line, and maybe that's a prescription for a motion of free string. Okay, so the corresponding action is called Nambu-Goto action for the string, and so we say that a free string motion extremizes the area of world line. Okay, so then, following exactly the same prescription, first thing what you have to do is that you have to be asking, what is my induced metric on this worldsheet? Okay, so similarly, we had like an induced metric on the world line, and we calculated the determinant of that metric, and that gave us the length of that thing. So now you have to be asking, what is the induced metric on that worldsheet? So first thing is to introduce the induced metric. So it will be two-dimensional metric, because now we have two dimensions. So it will not be just gamma lambda lambda, but it will be gamma AB. Gamma AB, it's 2 by 2 matrix. And it will be induced from the Minkowski spacetime, eta mu nu, right? And where, each index of the Minkowski metric is projected down to my worldsheet. The projector in this case is dx mu over d psi a, dx nu over d psi b. These are the projectors. So all you are doing is that you are projecting the indices of the Minkowski metric, you are dragging it back, you are pulling it back on your worldsheet. And this is your induced metric. Once you have the induced metric, you can calculate the area by taking the square root of the determinant of this thing here. and integrating over psi. So your action for the string x mu, so string, will be, well, here we had minus. Let's put minus. And then we had something like the mass of the particle. Okay? So the string has something like mass density or tension or something like that. And so there will be the corresponding tension of that string. And then it will be an integral of the square root of minus determinant gamma AB d square of psi. And that's what you have to do. If you want a motion of free string, this is the action. And it's simply like a square root of determinant. This is how you calculate volume, right? So in general relativity, you always put square root of minus g, right? d4x, whatever. So this is precisely what you are doing, except now you are doing for two-dimensional worldsheet. And this is your induced metric. So now what is this tension, right? So look at that. So here, let's say xi's have the right dimensions. Determinant, well, the metric components are typically dimensionless. So this has no dimensions, but you have d squared psi. So this has units of length square. Okay, the action. So now the action has to be dimensionless. So the t will have units 1 over length square, so that this is dimensionless. Okay, and so what people typically do is that they set t equal to 1 over 2 pi alpha prime, where alpha prime has units of length square, so that my action is dimensionless, and this ls will be the string length. Okay, so 2 pi is of course a convention if you want, but then your t has to have units of 1 over length square. So any length will do, but if you want to talk about fundamental strings in string theory, that will be the string length associated with that theory there. Okay, so this is the string tension. And this is it. So now what you have to do is that you have to vary this action with respect to x mu. You get some very horrible equations of motion, and you have to solve these equations of motion in a given space-time, and that will give you the motion of a relativistic string. Of course, you still need to provide some boundary conditions. You need to, so here, in case of particle, you have to provide, let's say, the initial position and velocity. In case of string, you need to provide how the string look like initially, but also you may need to provide what are the boundary conditions, what the endpoints are doing. Okay, and so we'll discuss that shortly. But anyway, so you not only have to provide the initial conditions, but also the boundary conditions for what the string is doing. But okay, and of course this you can generalize to any higher dimensional object. So if you don't have string, but you have a brane, right, which moves, then you have like a two-dimensional object which now moves in space-time, so a three-dimensional thing. So you have also more generally we have so-called p-branes. P-branes, and they have, well, we had word line, word sheet, so they will have word volume. Word volume. And if you have three p-branes, okay, so p stands for the number of dimensions. So how is this? If you have p equal to 0, that's the particle, right? Yeah. So p equal to 0 is the particle. P equal to 1 is the string. P equal to 2 would be a two-dimensional, like a brane and whatever, right? And so again, three p-branes will move in your space-time, according to this Nambu-Goto action, which is like you take the volume element on that word volume and you extremize that. Okay. Questions? Have you seen this in Rus course or in other course? Who hasn't seen this? Everybody's seen this, so it's so simple. Okay, very good. So we have that. So now this action here is super nice in the sense that it's super geometrical. It has very nice intuitive meaning. It is like, well, it really tells you I extremize the volume, right? Or I extremize the area. So these types of actions are called Nambu-Goto actions. This is geometrical Nambu-Goto action. Okay, Nambu-Goto action. However, it's not good for several reasons. If you, first of all, if you want to quantize this, well, you have to quantize something which is under the square root, and that's difficult. So this is very difficult. If you use the square root, it's crazy. And second, it seems like you cannot take the limit, let's say, for the point particle to mass goes to 0. If you send m0 to 0, then this action vanishes and doesn't tell you how massless particles actually move, right? So the way to cure this is through something which is an alternative to this Nambu-Goto action, which is called Polyakov action. By the way, this cartoon is the cartoon number 1. We will have 5 more about string theory, okay? So, alternatively, we can consider Polyakov action. Polyakov action. And let me write it for the point particle first. So now, S, Polyakov, and then let's say particle. So now you make it a little bit more complicated, but at the same time more simple. Okay, so here, your point particle action, the Nambu-Goto action, is just a function of the trajectory, x mu of lambda, right? So it's just one variable x mu there. So the Polyakov action will have 2 variables. It will have x mu, but it will also have like an induced metric on the word line. So now we have this extra variable h. So in that sense, it's more complicated. However, it doesn't have the square root. It's 1/2 integral 1 over h eta mu nu dx mu over d lambda dx nu over d lambda, that's my induced metric, minus m0 square h d lambda. Okay, so that's the point particle Polyakov action, where now both things here, x mu and h, are functions of lambda. Okay, so we have made it more complicated. Now we have 2 things to worry about, x mu and h, and they are functions of lambda. However, if you look at this thing here, the action is the standard action with respect to x mu, in the sense that it contains the derivatives of x mu and so on. But if you look at that, this is the h, there's no derivative of h. So there's only like an algebraic appearance of h. There is no any derivatives of h. So what this h is, truly, is not like a full dynamical variable. Rather, it's something which is called Lagrange multiplier. Right? So this is like a Lagrange multiplier. So there are no derivatives of h. Okay. So now this is crucial for how to show that this action is actually completely classical equivalent to that one, is that h is a Lagrange multiplier. If this was not the case, and h was like a full dynamical variable, what you would not be able to do is that maybe I can, so you know, you have to vary this action with respect to both. You have to vary this action with respect to x mu and vary with respect to h, right? If h was not a Lagrange multiplier, then if I write down the equations of motion for h, I cannot plug them back in the action because you would spoil the action principle, okay? You cannot do it. But if it's not a dynamical thing, it's just a Lagrange multiplier, you can do it. Okay, so then what you do is that you do the variation delta h. Okay, so that's very simple. So you have just 1 over h, that gives you minus 1 over h squared, minus 1 over h squared, and then this gamma lambda lambda, and then minus m0 squared delta h is equal to 0. Right, so you can calculate what the h is from here. Right, so from here, you find that h is 1 over m0 square root of minus gamma lambda lambda. Okay, now if you plug that back, now you can plug it back because this is not it's just a Lagrange multiplier, it's just algebraic constraint. Okay. So this is an algebraic constraint, it's not an equation of motion. So plug back. To the action. And if you plug it back to the action, look what's happening. So we have 1 over h. This will be complicated. Statement is, if you do it, so there's, okay, this one is simple. So you have m squared divided by m, h, square root of gamma lambda lambda. Okay? With a minus sign like that. Now the statement is this thing here will have exactly the same contribution. It will be exactly the same thing. You see it, right? I don't see it, you see it. So then this thing here, when combined together, precisely gives you back this SPP. Okay? So then we'll plug back and recover SPP for the point particle. Right? So what does that mean is that classically the two actions are equivalent. Okay? But, of course, this action, in some sense, is much nicer because it doesn't have any square roots. You just have, you know, it's actually, you know, it looks like an action for a scalar field here, right? I have dx mu, d lambda, dx mu. So it's quadratic in these derivatives. It looks like an action for free scalar field or whatever. Yes?
This action, it doesn't really look like it's reparameterization invariant, right? Because there's like, two d lambdas and these sort of things.
Yeah, exactly. So very good. So what you are saying here, look at this, right? I use a parameter lambda, right? If I use parameter lambda, well, if I use different parameter lambda, so if I use lambda tilde as a function of lambda, well, then I can put d lambda here, d lambda tilde, but that precisely cancels this, you know, under the square root, d lambda tilde, so I can reparameterize this. And this action remains of the same form, right? So this action nicely has reparameterization invariance. So here, this one, if I reparameterize lambda, well, I would have to do something else, right? And yeah, so like you're sort of losing this diffeomorphism invariance, right? Or the parameterization invariance, right? Using that. Okay.
I mean, it's just saying that h has also have to change, and
exactly,
which precisely qualify h as a metric.
As an induced metric on this one line, exactly. Yeah.
I don't know. It's normally called an auxiliary metric. It's not induced from a higher dimension.
No. Gamma lambda lambda is the induced metric. Yeah, this is like an auxiliary metric. That's right. Yeah. Very good. One more thing which I wanted to say is that in this form, so it's nice and quadratic. And second point, you can take m0 to 0. Can now take m0 to 0. Okay, now my action doesn't become 0. If I take m0 to 0, I just kill this term here, right? And then precisely what you can do is that you can say, well, h is a function of lambda, so you can absorb this h into lambda here, and then you would get a nice particle for massless, nice action for massless particles, which would just be eta mu nu dx mu over d lambda dx nu over d lambda. Okay, and can absorb h into lambda and get nice s massless. Should be like 1/2 eta mu nu dx mu over d lambda dx nu over d lambda d lambda. Okay, and that will be a nice action for massless particles in this way. Okay, so in some sense, the Polyakov action tells you, well, I can do it. I can set m0 to 0. So there's a nice and smooth limit to massless particles. It's more complicated here, right? Unless you say, well, absorb m0 into lambda and somehow take then m0 to. But anyway, so I think this is a nicer way to do to massless particles. Okay, so now by analogy, let me just write down what a Polyakov action for massless strings would look like. Okay, so then we have Polyakov for massless strings. So now S x mu, it will depend on this auxiliary metric on the worksheet. So the worksheet, well, sorry, this is the induced metric on the worksheet. It has the indices A and B. Auxiliary metric on the worksheet will have the same indices A and B, HAB, okay? And so this thing here, there is magic 1/2. Okay, there's magic 1/2. If you look at the point particle action somewhere, that doesn't have the 1/2. This one does have the 1/2. Okay, so there will be 1/2 with respect to the Polyakov action here. The Polyakov action had 1/2 pi, so that would be 1/4 pi. Okay, that's 1/4 pi alpha prime. There's a minus sign. And then integral d square of psi, square root of the determinant of this auxiliary metric, and then h a b gamma a b. Okay, how did I come up with that? So if you look at this thing here again, sorry, that thing there again, then it's 1/h. If h is a metric, 1/h is the inverse metric. We have an inverse metric here. And then we have this eta mu nu dx mu dx nu d lambda, which is this gamma lambda lambda. Now it's gamma ab, more general. This is how we arrive from there, here. Okay, so this is your Polyakov action for the massless string. Everybody happy with this? Yes.
So
if you go to the point particle case,
Uh-huh.
you write down a partition function for that.
So if you have,
If you write down a partition function, like integrating over all paths and h, is solving for the equation of motion and substituting for h the same as integrating out h in the path integral? Like,
is solving for,
So, yes.
okay, thanks.
I had a related question. Can you just take and quantize, treat it as a QFT with non-zero mass actually? What would happen? Like, we know we need actual fields to quantize particles. But here, like I'm taking a particle and actually, yeah.
I mean, people have quantized this action, so for sure, even with the mass. So yes, you can do it. Yeah. People have. Oh no, we have to finish. So let me stress one more thing here. So now, if I open this thing here, right? We have HAB is the metric in 2 dimensions, right? Is this auxiliary metric? Auxiliary metric. So now let me compare this action with something that you very well know. So if I were to write down the action, so compare to action of free scalar field, scalar in 2 dimensions. So how would I write the action of a free scalar field in 2 dimensions? So I would have S of the scalar field would be, well, let's say 1/2, doesn't matter, and then there will be a determinant of the metric in 2 dimensions. There would be HAB, and there will be gradient A of phi, gradient B of phi. This is just nabla phi square, right? This is just nabla phi square. But now I'm in 2 dimensions. Right? This is what you would know. How would you write action for a massless scalar field in 2 dimensions? But now look at what's happening here. What is this thing here? Well, this thing here is eta mu nu, and then it's d x mu over d psi a dx nu over d psi b. Or in other words, this is eta mu nu nabla a of psi mu nabla b of psi nu. Right? That's what it is. So if I take mu to be t, then I have one scalar field xt, and this thing here, well, so then this would be just like nabla square of that xt. But then would have also another direction, I don't know, x or y on z or whatever, 1, 2, 3, 4. So this is actually like an action for d scalar fields, x mu, right? Where I sum over these scalar fields with a weird sum. The sum is through the Minkowski metric. It's like a bunch of scalar fields in 2 dimensions in 2D. These scalar fields are x mu, right? But one of these scalar fields, is precisely the x01, comes with a different sign of this nabla phi square, right? All of them comes with a plus, but one of them, the zeros one, comes with a minus. So one with weird signature of the kinetic term. But basically, you can think about like this Polyakov action for the string as simply an action for d scalar fields and like the d free scalar fields. Okay. But if you are in 2 dimensions, scalar fields are super nice. Massless scalar fields are super nice. In particular, this action enjoys so-called Weyl symmetry. Okay, this has Weyl symmetry. do you know what Weyl symmetry is? You can rescale the metric by a conformal factor omega square. So I can go with HAB to omega square HAB. And my action will remain invariant. Okay, so if I do this, and my inverse matrix will go like omega to minus 2 HAB, right? And then determinant, I have 2 by 2 matrix, right? So the determinant will also be like if I want to calculate the determinant of H, then it will go like omega to the 4 HAB, but I take square root of that, so it will be like omega square. And I will have omega minus square coming from this guy, and you see that this is invariant. Okay, so this particular action has Weyl symmetry. Weyl symmetry is even stronger than conformal symmetry. Okay, so your theory of strings will have very nice symmetry, the conformal symmetry. And that's the cornerstone of string theory. Okay, so we have this Weyl symmetry just coming from here. Let me stop here. Questions?
How do you get the equation of motion for H?
How do you get the equations of motion for H? Well, you have to vary this action. What I'm saying here. Of course, I'm stupid. So this is S phi. Here, you have to vary both, right? You have, in the same way as we vary here, with respect to x mu and h, you have to vary both things here, right? So now what happens, right? So if I vary with respect to h, I get something like an energy momentum tensor, right? Right? So the variation has to be equal to 0. So the corresponding energy momentum tensor will have to be 0. TAB will have to be 0. That's called the Virasoro constraint. Okay, so that will significantly limit the solutions, right? And so that's what makes it non-trivial. Otherwise, you would have free scalar fields, right? If this were only your variable, then you would have just free scalar fields in 2 dimensions would be easy peasy, right? But the fact that you have also this as a variable, you have to vary with respect to HAB as well, right? Then you get that the corresponding TAB has to be equal to 0. That's a constraint that introduces nonlinearity. That's why you have nonlinear sigma model for string theory, right? So you have to vary both. You have to vary x mu, it's like a scalar field, free scalar field, but you also have to vary HAB, and that introduces nonlinearity into the play. More questions?
Is there some sign kinetic term of the one scalar related with the gravity side to the conformal mode problem?
I have no idea. Is it? So, well, certainly one of them is strange, right? One of them comes with a wrong sign. It looks like a tachyonic thing or whatever. I don't know.
What's the difference between the diffeomorphism invariance and the Weyl symmetry?
Very good. So here I'm not changing coordinates at all. Okay. So here all I'm doing is I'm rescaling the metric. I'm rescaling the distances, right? So of course in principle you can mimic. Well, if people consider conformal symmetry, right? So it's like a generalization of the Poincare group, or so then they do coordinate transformations which change your Minkowski metric up to a Minkowski metric with an arbitrary conformity factor. So in that case, you consider coordinate transformations and you enlarge your group of allowed transformations, right? This is a different, stronger symmetry. That one, we will have a tutorial on this. Don't worry. So that one, the conformal symmetry, is finite dimensional. It's a boring symmetry. It's like a Lorentz symmetry. This one is super nice and much stronger. Why is stronger? There's an omega here, arbitrary function. This is infinite dimensional symmetry. This is stronger.
Wait, when you say conformal symmetry, do you mean scaling symmetry? Because
As well, yeah.
but,
I mean,
but like some other people will define conformal symmetry to be diff cross, well,
to be what?
to be have both diffeomorphism and what?
Diffeomorphism and
While. While, your while.
No. Definitely not. So what conformal symmetry is that I consider coordinate transformations. I go from x mu to x mu plus psi mu, so that my metric eta mu nu goes to omega square eta mu nu, right? That's what conformal symmetry is, right? So then you may be asking, what are the allowed coordinate transformations and stuff like that? And of course, the allowed coordinate transformations will be all of the Lorentz group. I can do translations, I can do rotations and stuff like that, but I can also do the scaling, right? I can also go from x mu to lambda x mu and so on. So this will be conformal symmetry. While symmetry has nothing to do with coordinate transformations. While symmetry is I just change the distances in the metric. I rescale the metric. I don't do any coordinate transformations whatsoever. I just rescale the metric by omega square. And the question is, is my theory invariant under this?
No, I think it's like two sides of the.
In flat space, okay, we will have a tutorial. Let's stop the discussion here. But this one is stronger, okay? This one is stronger. If you have Weil symmetry in curved space, you will definitely have conformal symmetry in the flat space. Yeah.
Are these symmetries gates or global in string theory?
I should know that. I don't know that. They are fundamental symmetry. They should be.
It's gauged. We're gauging them in an hour. We're gauging the symmetry in an hour. So.
Yeah.
Why can it be global? It depends on space.
It's not the criteria in a quantum theory.
Oh, you mean the quantum theory?
But why should I gauge Weil symmetry? Reparameterization invariance, diffeomorphisms, I can understand that it's just a redundancy, but symmetry, why is it gauged?
What was that?
Because there are no global symmetries in quantum gravity.
Yeah. Okay. Let's postpone that. Yes.
Is this a comparison between the scalar fields and the coordinate x? Is that what motivated the, like in dilaton gravity, we can use the dilaton as the coordinate?
You can use, sorry, what? You can use?
And we can think of dilaton as spatial coordinate. Is that why? Is it motivated from this comparison?
I'm not sure. Well, certainly, here I'm just saying it looks like free scalar fields, right? That's all I'm saying at this point, right? And but one of them is a strange one, right? Why you can use dilaton? Well, dilaton you use. Okay, let's postpone this. Okay.